Okay, the directions for chemical batteries starts on page D67. It says put 25 milliliters of water into the plastic cup. Add 5 packages of salt. Add 25 drops of hydrogen peroxide. Stir until all the salt is dissolved. Carefully pour the mixture into the seed pup wet cell. This is the battery's electrolyte, the material that makes the liquid electrically conductive. So I'm going to take 25 milliliters, pour it into the cup, add the salt, and 25 drops of hydrogen peroxide. Straight up and down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. And stir. Until all the salt is dissolved. Next, we're going to pour the electrolyte into our wet cell. The next set of directions say to clip 1 wire lead onto the copper strip, and the copper strip is the one that looks like a penny. And then it says, let's see, this is going to go here. It looks like this. And then it says to, with another wire lead, put it onto the magnesium strip. Now, magnesium is this little tiny one. So we're going to take it, we're going to put it on like so. It says clip the other ends to the motor. Now the directions say to lower the copper and magnesium strips into the outside slots of the seed pup wet cell, and there should be a small amount of metal sticking out of the cells. So we're going to take the magnesium on one side and the copper on the other. We're going to look to see that the motor is spinning. So that is copper on the left, magnesium on the right. The next set of directions says to once the motor spins, disconnect the wire leads, remove the 2 metal pieces and dry them, then shine them with the piece of sandpaper. It's extremely important to completely dry the metals on a paper towel and clean both sides with sandpaper. So we're going to take this off. We're going to dry it with a paper towel, and then we are going to sand it with the sandpaper. Okay. Same for magnesium. And then sand it with sandpaper. Okay, the first part of the chart for part B says put copper and magnesium together. How many times does it spin around? And 10 times, and write your observations. So I am going to demonstrate each of these: copper, magnesium, copper and zinc, copper, iron, zinc, magnesium, zinc, iron, and magnesium and iron. Okay, that's what I'm going to demo right here. This is copper and magnesium. 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds. This combination is copper and zinc. It'll go a little bit with a little shove, but that's about it. Okay, this is copper and iron. This does not appear to be allowing that to spin at all whatsoever. Notice what's happening in the water in the wet saw. This is where the copper was. This is where all the other materials were. This trial will be zinc and magnesium. Zinc and magnesium. It'll go a little, but not even a quarter of the way around. Notice what's happening in here. This time around, we've got zinc and iron. This really doesn't want to turn at all, and if anything, it wants to turn backwards. The last trial is magnesium, which is this one, and iron, which is this one. Look at what's happening in here, and look at how fast that's spinning. Write your observations. In this next segment, I am going to use iron and magnesium, which cause the flag to turn relatively nicely. We're going to investigate the distance. We're going to start on the ends. So I'm going to take iron and magnesium and put them in. And as we go in here, we're going to take a look at our flag that's turning. I'm going to get it to go this way. And then I am going to move one closer, a little closer. What is happening to the speed of the flag? Also, you'll notice something's going on in there. So put your results and give an explanation for what you think is happening here. Okay, now we're on step 11, and we are going to reverse the connections. So you can see that I am still using magnesium and iron, and I am going to switch. Oops. to take this one off. And I'm going to go here and go here. Let's see what happens. What happened? This is going to be step 12, surface area. So if we have a little bit, I'm going to put them right next to each other. I have magnesium on the left and I have iron on the right. And we know that when we put it in here, so surface area, if it's just a little bit in, doesn't do much. If we are down farther, it goes a little faster. Down, 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 all the way. So if we don't put it in very far, it goes slow. And if we put it in all the way at the bottom, it goes much quicker. Record your observations. So we have a few analysis questions to answer. And the first one is number 1. And it is for chemical batteries. It says, was there a chemical change when you inserted the strips into the electrolyte? Describe any evidence that supports your answer. How did you know that a chemical change actually took place? Think about that and write your answer. Hit stop so that you can complete your work and then pick it back up when you're ready to go to the next one. Take a look at question 2. It says, use your results from part B to rank the metal combinations from 1 to 6, with 1 as the highest releasing electrical energy rate and 6 as the least. Describe any evidence that determined your rankings. So the first one is magnesium and copper. Second one that they listed is magnesium and iron. The next one they listed is zinc and copper. Next one, zinc and magnesium. Next one, zinc and iron. And the last one they listed was copper and iron. And what you are to do is to give them a rank. Which one had the highest releasing electrical energy charge? That would be your number 1. And the one that had the least amount would be number 6. Answer that now and hit stop. The next question says, look at the table below that describes the reactivity of the metals used in this activity. Compare the table to your response in analysis question number 2. Based on the comparison, does reactivity alone indicate what combinations of metals will release the most energy? What patterns do you see that could indicate why the most and least energy combinations occurred? C. Gold is the least reactive metal known and tends not to give up electrons. Which metal from the table would you pair it with to make a strong battery? Explain your choice.